So in the last class, we have discussed about several coordinate systems, Cartesian coordinate and the uh, cylindrical coordinate systems. So, so I think we stopped at the point of spherical coordinate systems. So in the spherical coordinate systems, we'll be talking about its parameters and how we can define its coordinates with respect to x, y, z coordinate systems. We will discuss it during this class. After that, we will start the sections about the electric field and electric field related concepts. So, so let's begin with the spherical coordinate systems, and we will try to study about that content first. So, so as we talked about the Cartesian and the cylindrical coordinate systems, which are important in several applications. And the spherical coordinate system is also important for applications such as antenna design and evaluating their performance, antenna performance. So once we consider the radiation of antennas in the space, so we tend to use the spherical coordinate system to understand about the radiation of the antenna in the directions of the in the space in terms of the coordinate axis of the spherical coordinate system. So that is one of the advantages of the spherical coordinate system, where we can learn about how where we can learn about the radiation of the antenna. So you have asked a question regarding attendance, right? So do you know about the tool that that SLT has provided you, SLTC has provided you to mark the attendance? Because there's a tool. In that tool, you just need to log in with your SLTC email. And once you have login, you can, I think you can, you will see, uh, you will see a place where you need to enter the OTP code. So actually, I don't have a link. You need to log in with your own email, and then you need to select the course, the module, and then you can mark the attendance using the OTP. Also, I have the QR code. If you need that, I can share that with you as well. You know about this tool. Actually, I will share with you the screen of that tool. For me, for my end, this is what is shown. In your screen, you need to see a session. With all the data, and then in there you will have a option to put the OTP code. I hope you are okay with it. If not, your attendance will only be marked from this tool, and the OTP code is valid for 30 minutes only the first 30 minutes. So after it expires, you can't mark your attendance. Apart from that, I don't know how they are going to like evaluate the attendance in this semester. If they decide that they are going to consider the attendance of the students at above a certain limit, then you need to mark your attendance. So this is a kind of important task. So if possible, please try to get it done. If you don't know how to do it, then I think you can ask from your friends who are in this meeting, and then ask from them how to do it. I think they will let you know. Also in the meeting, I think you can find the regular students. From them, you can ask and you can verify how it is done if you require. Right? From my end, I really do not know how it is done from your side. So let's resume the spherical coordinate system uh, explanation. So spherical coordinate systems uh, can be used to analyze the radiation of antennas and understand the performance of antennas and so on. So we are normally using plots like this to find the radiation of an antenna, for example. So we are considering azimuth plane, we are considering elevation plane. So those planes are defined for the spherical coordinate systems. Okay, so we will therefore talk a bit about the spherical coordinate system. As usual for the coordinate systems, we need to define, we can define the line element, surface element, vector surface area element, volume element of a coordinate system. So for the spherical coordinate system, we have the setup like this. So we have the angle that we measure from the x-axis towards the location that we are considering. So in here we are considering a location given in this point, uh, which is this point, this specific point we are considering, and then we are trying to give its location based on the spherical coordinate axis. This specific point we can define using the unit vectors along the axis of the radius axis, the phi axis, and the theta axis. So basically, the unit vectors will be given as in this figure. So radially, we can have a unit vector along the radial direction. Then we can have a unit vector along the phi direction. Then we can have a unit vector along theta direction. Right. So afterwards, we can define the line element, surface element, vector surface area, and the volume element. Right. So this is a very visual thing. So in order for you to understand it, you have to draw the coordinate system by yourself. Okay, so in order for you to define the line element, you need to consider the increment of a certain point along each axis of the coordinate system by a very small amount. Okay, so you need to move a dr distance along the r direction. You need to move dr amount along the r hat direction. You need to move a small distance along the phi hat direction, phi angle direction, which we measure from the x-axis. Okay, so phi is measured from the x-axis, right? So we need to move a small distance from the phi direction. That length is not phi d phi. It's not d phi because it is a angular direction, angular distance. So it's an arc. So we have to move a arc distance of uh, r sine theta d phi. Okay, so we will talk about this later. I will just mention now. So then we have to move a small distance of r d theta along the theta hat direction. So because this is also, distance that we move along the theta hat direction is also an angular distance, which we can represent using an arc length, right? So based on all that, we can define the line element, right? So line element we can define as the sum of all the incremental distances we have moved along each of the axis in the coordinate system. All right. So one student is telling about not having access to the attend on. Well, I actually I need to really ask that from the registrar office. So anyway, uh, then I think I will mention about this issue to the registrar office via email. If possible, you also mention that to the registrar office. Okay, because otherwise there's no way of informing about not like allowed you or your they have not given you access still. I think it's something that they have to do by now. So I will ask from them what is the issue, and so for so actually I'm also in a problematic mode because I need to show that I have I have done the class and you have attended the class. So I don't have any other proof. I will resolve this issue by getting a call to them, and I will ask from them. I will get back to you about this in the next class. But in the meantime, I request you to send an email to the registrar office. If possible, do that. So for today, it's okay. You can go ahead without marking the attendance, but if possible, please send an email to the registrar. So line element we can define as the sum of the incremental distances we have moved along each of the coordinate axis, right? So I think I will get some figure to explain this. So you also can try to visualize the coordinate system by drawing the coordinate system in your own books and your papers. So coordinate system, spherical coordinate system is actually a little bit challenging than Cartesian coordinate system. So we have the xy coordinates, xyz coordinates as usual. And then if we want to mark the location uh, of a certain point, let's say A or something in the space, we we can use the spherical coordinate system to mark its location. When we are using spherical coordinate system, we need to use three parameters basically. So this is the origin of the coordinate system. So first we need to consider the radial direction, the radial distance from the origin towards to that point A, right? So that is one measurement that we will take. So this point A, let's assume we know the letter of that point. So the magnitude is given by R and the direction is given by R hat, right? The unit vector along the direction of R vector. We will we will mention that the vector to this point is R hat, R vector. Unit vector along R vector is R hat. So one parameter is R vector, right? R vector. Then we have the angle that we can define for this position along the xy plane, which we define using phi. So we have, so my art is not that good. I hope you can visualize it. So you need to mark the angle of this point. Let's say this is the angle that we have from the x-axis direction to the point that we are considering. So this angle we can define as phi. Then we also need to define the theta angle in order to define in what elevation this is in, right? So in order to define the elevation, we need to define the theta angle, which is defined using the angle that is created by the z-axis up to the point that we consider. So this theta angle, it is a like an angle that we can measure from the z-axis to any point in the space. So you can visualize in a 3D manner. So this theta angle is something you can measure at any point with respect to the z-axis. Okay, so I hope it is clear to you. If it is not clear, please let me know. So this point we can define using r, phi, and theta. So we can give any value to r, phi, and theta. Based on that, we can define any point in this coordinate system using these three parameters. So once we are defining something called line element uh, is the vector that defines uh, the the vector which is formed once we move a small distance along each of the coordinate axis, right? So the total vector that we get by moving a small distance along each of the axis uh, is the line element. Okay, so in that case, a line element we can define as the smallest distance we can go along r vector is dr, right? So dr into r hat plus the smallest distance we can travel along phi hat direction is is something that is new in here. So I hope you can follow me along in that. So the smallest distance we can go along the phi direction is given by the radial, uh, the, the, the smallest distance that you can go along this direction, in the angular direction, right? So the distance that we can measure in the angle that we have traveled is d phi, right? Angle that we have traveled is d phi, right? And the distance that we travel in this instance is uh, given by this radius into the angle. This is what that we are traveling this time. Right. So what I'm saying. I don't know whether you are understanding the things I'm saying, because you are not answering the questions, and I feel whatever I'm teaching is not that clear. Right? I know this is a difficult section, and maybe the artwork that I'm doing is not that clear. So if you're not like if you cannot understand, please let me know. Right? I like to give you time to respond in this case, right? So Randimal, I think you are a regular student. So can you please just wait a little bit, because I think I need to wait for the answers from the other students who are doing lateral entry program. So they are actually they are doing this class for the first time. Since you have already done this section, I think you need to just wait a little while, because I have to wait for them to understand this section. So other students, can you please let me know whether you are okay with this or not? Because I think this is a little bit difficult. I totally understand. It's just that I need you to understand the visual concept here, and just define the line element, the surface element, volume element, and so on. So these like mathematical things will be useful for like later sections of this module. We'll be covering some content related to dipole antenna and so on. So in that case, we will be requiring this content. So that is why we need to get some understanding about this coordinate system. So for that, I'm covering these sections related to these definitions. So the line element, we can go ahead with the definition that the vector that we can create once we move a small distance. The vector that we can create once we move a small distance, small infinitesimal infinitesimal distance along each of the axis, right? So the vector that we can create once we move an infinitesimal distance along each axis, and once we take the sum vector, like the sum vector that we can create once we move infinitesimal distance along each coordinate axis is what we define as a line element. So when we define the line element, we need to go along the axis, coordinate axis, r, theta, and phi. So r axis, we can go along the r axis distance of dr. Dr is the smallest distance we can go along the r hat direction, right? So the smallest distance we can go along the phi direction is the angular distance we can move from the starting point towards the phi hat direction. So phi hat direction is the tangential uh, tangential distance we can move along the phi hat direction, right? So phi hat is the unit vector along phi direction. So if you can't understand, please let me know, right? So in order to find that distance, we need to take the small arc length that is formed in here. So the arc length that we can form is given by r sine theta, because we need to take the projection of the of the of the of the r vector on this xy plane, and then we need to multiply that with the d phi amount. So so this is the radius, and this is the angle that we will be moving. The angle of the incremental angle that will be moving along phi direction will be d phi. So this is the angle. So we need to take the combination of the radius and the angle to get the arc length. So arc length is in the smallest distance that we move along the phi direction. Smallest distance along the phi direction. And then we have the theta, and the smallest distance we travel along theta direction, we need to define. I think I will write this again. So the line element we can write as dr. So the line element I can write as dr into r hat plus r sine theta d phi into phi hat direct. Theta direction is measured from the z axis, right? So the theta we measure from the z axis towards the point of consideration. So we are considering this point, and we can measure distance hat direction. So distance we can travel along the theta hat direction, we can take again as an angular direction, angular distance. So that angular distance we can define using an is r, right? R and d theta, right? So r is the radius, d theta is the angular increment. So the total distance that can be given using r d theta. The total distance we call as arc length can be given as r d theta. So r d theta into d theta hat gives the total distance that we can travel along the theta hat direction. So this expression gives us the line element of the spherical coordinate systems. Line element of the spherical coordinate systems, right? So anytime we can define that line element is this expression for the spherical coordinate systems. So this is a standard expression, right? So dr, d phi, d theta, those are standard expressions for the spherical coordinate system. And you can define this as the line element for the spherical coordinate system. So this is something general for any scenario. It is not something we need to define explicitly for a specific case. We can use this as the line element if we require for any scenario. So basically, that is about the line element, right? So I will clear the drawing, and next we have to discuss about the surface element, right? So the surface element is surface elements that we can create by taking the perpendicular product between the line element components along the coordinate axis, right? So I will do this comment. So if you cannot understand even after referring these content, you can let me know. I will explain again. So for the moment, I will go like this. So if you have questions right now, you can ask. Otherwise, later also you can ask when you want. So the surface element is very easy actually. You just need to take the perpendicular product. You just need to take the product between perpendicular elements in the line element, right? You need to take the product of perpendicular components in the line element. So the perpendicular components in the line element are dr, r sine theta, d phi, and rd theta, right? So the surface element, therefore, three surface elements we can define. So surface element is formed by uh, creating the 3D object that is formed once you move a certain small distance along each of the coordinate axis, right? I will show you that basically that diagram. So this is the cube that we can form once we move a small distance along each of the coordinate axis of the spherical coordinate system, right? So if we are starting from a certain location, if we start from this location, we can go a small r d theta distance or along the theta direction, right? Along the theta direction, we can go r d theta distance, right? Along the r direction, we can go a dr distance. Along the phi direction, we can go a r sine theta, d phi direction, distance, right? So by going along those distances along this axis, we can form a cuboid of this shape, and we define the areas of this shape, uh, the surface areas of this shape as surface elements. So for a cuboid, normally there are three different, for this cuboid, there are three different surface elements, three distinct surface elements. Right? So those surface elements we can write uh, easily. So one surface element is the r d theta, into dr, right? Dr. So surface elements we take by taking the product of two perpendicular components, right? Right. So perpendicular component product we take as the surface elements, right? So r d theta and dr are perpendicular components. So we take the product of those components, and that is one surface element, right? That is one surface element. Another surface element is r sine theta. Element we can call as a phi or something, right? I will just mention why I have mentioned a phi. Another surface element is r sine theta d phi into dr, we can say, right? Dr. So that one we can define as a theta, and then we can define ar. Ar we can define as uh, r d theta into r sine theta d phi, right? So surface elements are like this, and once we take the vector surface elements, vector surface areas, vector surface areas, we just take the multiplication this area with its normal vector, right? So r d theta dr into phi hat, right? And then a theta is the a theta vector. A theta vector is given by the a theta into its normal vector. So a theta into its normal vector is theta hat. So r sine theta d phi dr into theta hat. So I mean, so ar vector will be r d theta r sine theta d phi into r hat. Let's see whether it is the case. Okay, so like we need to verify whether our what I have written actually is correct. So I will go here, right? So this is the line element vector dr, which is a vector, and then for finding the surface area elements, we take the product between the perpendicular components. Okay, so once we take the product between perpendicular components along the theta hat direction and the phi hat direction. This these two components, I can define the surface area element given in here, DAR, right? So this is the surface area element, DAR. And then surface area elements along, along, once we consider the surface area element which is perpendicular to the theta direction, I can take the product of components along the r hat direction and the r sine theta d phi directions. The product between those components I can define as the area element which is normal to the phi theta direction, right? So this must be confusing when you listen to it, but once you try it on your own, you will understand it very clearly, I think, right? So you can just visually you can try to draw the coordinate system on your own, and then you can try to write these expressions on your own, right? And then da phi we can define as the product between the components along r hat and phi hat directions, dr into rd theta. So that is how we define the surface elements, right? So once we are defining the vector surface area elements, we need to take the magnitude in here and multiply it with the normal vector. Normal vector. So normal vector is along the r hat direction, right? So the normal vector, so the vector surface area DAR is r d theta, r sine theta, d phi into the normal vector along that surface, that is r hat. Next, dA theta, the vector of dA theta is dr, r sine theta, d phi into theta hat. Next, phi. dA phi is dr, r d theta and phi hat, right? So basically what you need to understand is that if you are trying to find the vector surface area, you need to take the area of the surface and then multiply it with the vector which is perpendicular to that area, right? So if I draw a area like this, right, there's a vector which is perpendicular to this area, right? So that vector could be r hat, it could be phi hat, it could be theta hat, right? So depending on the normal vector of that certain specific surface area, we multiply that surface area with the normal vector, right? Surface area with the normal vector multiplied by the normal vector will give us the vector surface area. So I hope it is clear to you. If you have any questions, please ask. These are mathematical things, really. So might be not be clear to you at once. So once we want to find the volume element, it's very easy. What do you need to do once you want to find the volume element? I think you can explain that, right? You can you can let me know how you find the volume element, right? What do you need to do? What do you need to do in order to find the volume element? What is the product that you need to take? So students who are in this meeting, can you please answer? Uh, the lateral entry students especially, just give me the idea about how to find the volume element. So So since you are not answering, it seems you haven't understood anything, right? So on the perpendicular components of the line element are dr, rdt, once you consider the product of all those elements, we can find the volume element of the smallest area or smallest volume that we can create in this coordinate system, right? So to you before you. So this diagram shows the smallest volume that we can define for the spherical coordinate system. So the volume of this element, this cuboid, the sides of the volume, right? So there are three different sides which are distinct to each other. So those three different sides we consider in order to take the volume element, right? So we need, so with those we can find the volume of this cuboid, right? So you need to understand that. So like so we need to multiply the uh, perpendicular components of uh, this cube, and we can find the volume element or the volume of this small cube. So volume element is taken by taking the product of dr, r d theta, r sine theta, d phi. So once you take that product, you will get this expression, right? I hope it is clear. So another explanation, or like another aspect to this coordinate system, is that we can move from one coordinate system to another coordinate system. Once we take the spherical coordinate system, we can find the value of r with respect to x, y, z coordinate systems. Once we take the x squared, y squared, and z squared and square root that, we can find the magnitude of the z radial distance. So r distance, right? So r vector, the magnitude of that vector, we can find using the xy coordinate values, right? XYZ coordinate values of the point. If we want to translate XYZ coordinates into r, theta, and phi coordinates, then we need to use these equations. Also, the theta angle we can define using the cos inverse of z over the square root of x squared plus y squared plus z squared, right? So since the cos theta value, cos theta value will give the z height, z value, right? Z value will be given by once we take the projection of the considered point on the z axis. So once we take the projection of this r vector onto the z axis, we will be left alone with the z value, and the angle will be given by z over r. Will be equal to cos theta. So in order to find the theta value, we need to take the cos inverse of z over r magnitude. Then in the phi angle, we can define using y over x, tan inverse of y over x. So I mentioned that phi angle is defined in the xy plane. It does not have any relation to z plane. So not related to the z axis. So its value purely depends on y and x coordinates. Right. If you have any questions, you can ask. Apart from that, we also have a a way of translating the unit vectors along all along three coordinate axes onto the unit vectors of the x, y, z coordinate axis. So you know that the unit vectors of the spherical coordinate system is uh, r hat, phi hat, and theta hat. So so we know r hat. Uh, we are now trying to find r hat in terms of I hat and j hat. I hat and j hat, k hat are unit vectors along x, y, z directions. And theta hat we can find also with respect to I hat, j hat, and k hat. Phi hat also we can do the same thing. We can find along I hat, j hat, and k hat, right? So one special thing we see is that phi hat is only related to I hat and j hat directions, right? So as I said before, phi is not related to z axis, so it's not related to k hat. It's not related to k hat. So because of that, phi hat is not defined using k hat. Phi hat is defined using I hat and j hat components. So what is done in these figures is that you can define the vectors along each of the coordinates using I hat, j hat, and k hat vectors, right? So basically, you just need to find the projection along the x, y, and z axis, and write that using and multiply it with I hat, j hat, and k hat. So I will quickly mention how they have done for the r hat. So r hat vector we can take like this, starting from the origin to the point that we are considering. So once we want to take the projection along x, y, z directions, we need to take first the projection onto the xy plane, right? So we take the projection onto the xy plane. So the projection will be of magnitude r sine theta, right? So since we are considering unit vectors, we are only going to consider the magnitude as 1. So 1 sine theta, right? So 1 sine theta is the length of the from origin, right? So once we take the projection onto the xy plane, we have a distance that we have from origin to this point, and that length is sine theta, because we are taking so if we take r magnitude is 1 in here, we only take sine theta, right? So r hat magnitude into sine theta is again sine theta. So sine theta, so sine theta length we know. Now we can calculate the projection along x direction is r sine theta cos phi. The projection along the y-axis we can take as r sine theta sine phi, right? So along the I hat direction, r sine theta cos phi magnitude is available. Along the y direction, so along the j hat direction, we have r sine theta sine phi magnitude. And once we take the projection along the z axis, we have r cos theta, right? R cos theta, since r hat magnitude is 1, we will have cos theta magnitude along the z hat or k hat direction. So by taking the combination of all those components, we can write that the location here, given here, can be represented as the sum of the components along I hat direction, j hat direction, and the k hat direction, right? So along the I hat direction, the magnitude is sine theta cos phi. Since r is 1, we can we can forget about r. We can remove r. So magnitude along I hat will be sine theta into cos phi. Magnitude along y hat for j hat will be sine theta into sine phi. Magnitude along k hat will be cos theta. Likewise, we can do the same thing for the other two coordinate systems, coordinate axis as well. For the theta hat, we can do the same thing. In there, we have the theta hat for the general vector that we are considering. First, we need to take the projection of the theta hat. I mean, the vector which has the theta hat unit vector onto the xy plane. So we can take the projection as cos theta, and then cos theta we can divide into xy axis as cos theta cos phi, right? So this is going to be cos theta cos phi. This is going to be cos theta sine phi, and the projection along the z axis direction will be minus sine theta. So they have considered the theta hat direction along this direction. So the projection onto the z axis will be sine minus sine theta. So this length anyway will be sine theta. So by taking the combination along each of the axis, we define the theta hat as the combination of cos theta cos phi I hat, cos theta sine phi j hat minus sine theta k hat. Right, so depending on how we define the theta angle, we define the theta hat vector like this. Next, we have the phi hat unit vector. Phi hat unit vector we can define using the components along the xy coordinate axis. Right. So once we measure the phi angle in this manner, we have the projection along the y hat direction as cos phi, and along the I hat direction as minus sine phi. So depending on the angle and how we define it, we can determine the phi hat unit vector along I hat and using I hat and j hat vectors. So that's basically regarding the spherical coordinate system. So we will end the discussion about coordinate system with that. If you have any questions, you can let me know. Apart from that, I have mentioned that I have provided document in the LMS regarding the coordinate systems. So you can refer more about those, coordinate systems using that document available in the LMS, right? So please refer that if you have questions regarding the coordinate systems. So, so next we have to, talk about the electric fields and the magnetic fields, right? So basically now we have covered the fundamental concepts related to vector calculus. And from this lecture onwards, we are going to dive into the details regarding electric fields and magnetic fields. So electric field and magnetic fields form the fundamental concepts of this electromagnetism course. Right. So basically, I will give a small introduction. I think we will discuss further in the next class onwards regarding the electric field. Right. So I think because I have discussed a lot about the spherical coordinate system, I think you will not be able to grasp or just, have all the information in your head today itself. So maybe we can discuss the electric field and its explanations in the next class. However, I will explain a little bit about the beginning of that lecture with the history. Actually, in the I think as I remember in the 18th century, the scientist called Coulomb, who was a French scientist, was able to find and present a law called Coulomb's law. So in that Coulomb's law, he mentioned about the forces that can occur between charges, and how we can define the force using the values of the charges and using the distance between charges and the Coulomb constant, a Coulomb constant. So he was the first person to identify electric field and define the electric field. So next comes Gauss's law. So Gaussian law also mentioned mathematically how electric field will behave in closed surfaces and how we can define the electric field that can be generated using a closed, theorem. So the electric field that is generated due to a electric charge, which is stored inside a closed surface, is equal to the total charge inside that closed surface. So that theorem was introduced. It is a very popular theorem. Next, we have Ampere's law, Faraday's law, Lenz's laws. Hans Ørsted also brought some principles. So those, the Ampere's law concepts related. So we'll look at the Coulomb's law and Gaussian law, and next we will look at the Ampere's law, Faraday's law, and Lenz's law. So, so the problem that we were having at that time was that were not unified. So, a scientist called James Clerk Maxwell was able to combine the principles of all the laws related to electric field and magnetic field and present a unified law regarding electromagnetic waves. So he was the person who presented the exact behavior of electric field and magnetic field working together. So therefore he's actually the person who introduced the electromagnetic theory. So this electromagnetic theory was born before the circuit theory. So circuit theory, which we use to analyze circuits and just do the Kirchhoff's voltage law and Kirchhoff's current law, was born before after the introduction of the electromagnetic theory. So electromagnetic theory formed the foundation for electrical engineering and electrical systems actually. So basically, according to my understanding, and so basically electromagnetic theory was able to like define the behavior of electrical circuits. So we'll be talking about the electric charge Coulomb's law in the next class, and how the force is defined based on the electric charges distribution in a certain space, right? So we will be talking about electric charges, their properties, and how electric field is created between charges. So in the next class we will do that, right? So in today's class we basically uh, talked about the spherical coordinate axis, and we discussed how we can define all those parameters related to spherical coordinate systems, right? So basically spherical coordinate systems we are important for us once we analyze antenna systems and so on. So uh, so basically, spherical coordinate systems are defined by three parameters: the radius to the point from the origin, the angle that we can measure from x-axis to the point, and the theta angle that we can measure from the z-axis to the point. So we define how we can write the mathematical equations of the line element, surface element, and the volume element of the coordinate system. Also, we discussed about how vector surface area is defined for that coordinate system, vector surface area. Then we also learned about how we can uh, convert from the spherical coordinate system to the XYZ coordinate system, and from XYZ to the spherical coordinate system, right? So if we have the XYZ coordinates, we can find our phi and theta coordinates using the XYZ coordinates. Then we also learned how we can define the unit vectors along the uh, r, t, phi, and theta directions. Right, so those were the things actually that we have covered in this lecture. So I hope you got some idea. So in the next class, I will discuss about the electric field and the related concepts for the Coulomb's law. Uh, so the Coulomb's law, and we will discuss about the electric charges and their properties little bit. So with that, I would like to end today's class. So if you have any questions, you can ask. I will stop the recording.